Welcome to MEC 416/816 or Engineering Acoustics. In this lecture, we're going to start Chapter 1, which is on single degree of freedom oscillators. We're going to start with the simple harmonic oscillator. So in this case, we're going to consider the following system. I'll just draw a ground here, and then here is a spring that connects to some block. We'll give the block some wheels so that it rolls on the ground here. No friction here, so we're ignoring friction. Block has a mass of m, spring has a stiffness k, and we're going to measure the displacement of this block with the variable x, and it's a function of time. So I just want to let you know that note that the book uses s, the variable s, for stiffness instead of k. So with that being said, if you're reading the book, you'll note that k is equivalent to s. Okay, so from Newton's second law, we know that the mass times the acceleration is going to be equal to the forces acting on the system. So the acceleration here can be rewritten as the second derivative, or d squared x over dt squared. So that's the second derivative with respect to time. And we can write this in a compact form as x double dot, where the dot represents a derivative with respect to time. And this is then equal to the force from the spring, which would be minus k times x. And this x double dot, that's our acceleration. So in this class, we're going to encounter two types of derivatives: derivatives with respect to time and derivatives with respect to space, generally. So whenever we have a derivative with respect to time, we're going to use dots, and for derivatives with respect to space, we'll end up using primes. In this lecture, we're only going to look at derivatives with respect to time. We might see a few other derivatives with respect to other variables as we go, but we're primarily going to see derivatives with respect to time, and therefore we'll end up using dots. So from there, we can obtain our equation of motion, or the governing equation of motion, which is going to be m times x double dot plus kx, and that will be equal to 0. And that right there is the equation that governs the motion of this oscillator. From there, we're going to divide by m, and we'll get the following: x double dot plus omega sub 0 squared times x, which will then be equal to 0. And here, omega 0 squared is equal to k divided by m. And omega 0 is what is known as the natural frequency of the oscillator. It's the frequency that the oscillator wants to move at. All right, so now that we have a differential equation, we want to solve this so that we can find the displacement, or x, as a function of time, so that we can predict the motion of this oscillator. To do that, we need to provide an Ansatz. And an Ansatz is just a German word that means an educated guess, meaning that we're going to guess the form of our solution. In this case, our Ansatz, we are going to say is that x of t is equal to a times e to the lambda t, where a is some amplitude, and then e to the lambda t represents some kind of oscillation. From there, we can take derivatives twice. We'll get that the velocity x dot is equal to a times lambda times e to the lambda t. And then from there, we'll get that x double dot is equal to, we'll put the lambda in front, lambda squared times a times e to the lambda t. From here, we're going to plug in our Ansatz into equation 3. And that's going to result in the following. We're going to get lambda squared a, let me rewrite that, lambda squared a times e to the lambda t plus omega 0 squared times e to the lambda t, and I've left out an a, let me add the a, omega 0 squared times a times e to the lambda t, still equal to 0. That's our equation 5. So we're going to make a few manipulations here. First, we can pull out both an a and an e to the lambda t, and then we'll get the following, that lambda squared plus omega 0 squared, all of that times e times a times e to the lambda t. All of that is now equal to 0. Since this must be true for all time, and e to the lambda t can only be 0, provided that lambda is negative, it can only be 0 for an infinite time, and a is non-zero. If a is 0, then we get back a trivial solution, which is not what we're interested in. In other words, we get a boring solution. So what that means is that the quantity lambda squared plus omega 0 squared, this must be equal to 0, which then tells us that lambda must be equal to plus or minus the square root of minus omega 0 squared. From there, we can deduce that lambda 1, 2, so we're going to have two lambdas where the plus and minus comes from, is going to be equal to plus or minus j times omega 0, where j here is our imaginary constant, or the square root of -1. And therefore, we now have the lambda values. Now that we know the lambdas, we can also then find a's. Lambda 1 is going to give us some a1 value, and lambda 2 is going to give us an a2 value. So we're going to get, for each of these lambdas, we're going to get a corresponding a. Then based on this, we can write that the general solution is x of t is equal to a1 times e to the j omega 0 t plus a2 times e to the minus j omega 0 t. And this is the general solution to that governing equation. With that being said, I'd like you to pause the video here and think about how can we find A1 and A2. Do we have enough information to find them? And if not, what is missing? Just pause the video, think about that for like 30 seconds or a minute, however long it takes you, and then come back. Okay, so although this is the general solution and it tells us what this, the solution is and what the displacement is, the problem is that we don't have enough information to determine what the constants A1 and A2 are. And that means that the problem is what we would say is it's not well posed. Meaning that A1 and A2 here can be anything, and for a problem to be well posed, we need to be able to produce a unique solution. In this case, we can't produce a unique solution because A1 and A2 can be anything. So that being said, we now want to consider a well-posed version of the same problem. And to that end, we need to prescribe what are known as initial conditions. So I'm just going to write that out down here. First, we're going to write the equation of motion again. So we have x dot plus omega 0 squared x. That's equal to 0. That's our governing equation. And now we also need to prescribe some initial conditions. We'll say that x of 0 is equal to x sub 0. And x dot of 0, we're going to say is equal to some u0. And in fact, we'll put, this should be number 7. You can write it at the bottom of page 1 or at the top of page 2. It doesn't really matter. I'm just going to erase the 7 there so we can prevent any kind of confusion. So I want to just say a quick comment about initial conditions. So here we're prescribing the starting state of the oscillator through the constants x0 and u0. You don't necessarily need to prescribe what happens in the beginning. You could say that the displacement is this value at some time, or the velocity is some this value at time, or both of them at some time, and then you could go backwards and determine what happened in the beginning. What caused this, caused those conditions to arise. So you can run the equations or the physics backwards and go there, and then you could also start at some non-zero time and then run them forwards as well. But generally, if we're given some conditions at a non-zero time, we will generally shift time and call that our new zero so that we still have initial conditions. Okay, once we have these initial conditions, we can then use them to find A1 and A2. We do that simply by substituting them into the general solution. We also need to take a derivative, find the velocity term, and then we can set it equal to there. By doing that, you end up finding that a1 plus a2 is equal to x0, and a1 minus a2 is equal to u0 divided by j omega 0, and we're going to actually want to bring that j up to the numerator, and in which case we get minus j times u0 divided by omega 0. Plugging these in, we'll end up finding that a1 is n equal to 1/2. Sorry, we're not plugging these when we have two equations here and we have two unknowns, that's a1 and a2. We're now going to actually solve for a1 and a2 using whatever kind of method you want. You could solve for you could use this, for example, the second equation, solve for a1, and then plug that into the first equation, and then solve for a2, and then go backwards, or whatever you want to do. So we end up finding that a1 is equal to 1/2 times x0 minus j times u0 divided by omega 0. And we can see here that a1 is now a complex number. And we end up finding that a2 is equal to 1/2, and it's going to be the complex conjugate, which is x0 plus j times u0 divided by omega 0. And those are our two constants. We're going to end up dealing with complex numbers in this class. If you don't have a lot of experience dealing with complex numbers or complex variable theory, you should do some review on that and learn some of the basics, or come speak to me either through Discord or reach out to me. Reach out to me in Discord or come to office hours. And if you can't come to office hours, we can schedule another time. So at this point, now that we've found a1 and a2, we're now going to plug those values into the general solution. We'll then apply some identities, particularly Euler's formula and so forth. And by doing so, we'll get that the displacement x at t is equal to x0 times the cosine of omega 0 times t plus u0 divided by omega 0 times the sine of omega 0 t. And that right there is our full solution, the displacement that is unique and depends entirely on those initial conditions. Okay, that's what we want to say about simple harmonic oscillators without any damping or any applied force. We're now going to do an example problem, and then we're going to look at damped motion and talk a little bit about what damping is. Okay, so in this example, we are given that the block has a downward speed of 2 meters per second as it passes through its equilibrium position. So there's no gravity included in this problem. The diagram is shown on the left here. So because there's no gravity included, the equilibrium position is going to be 0. And the x here, that is drawn as being measured as the motion away from 0, or the equilibrium point. So let's just add a little note here. We'll do it in purple. This is our equilibrium point. We'll say equilibrium position. Okay, we now are asked to find the maximum acceleration of the block over one cycle of oscillation. And we need to use that the stiffness, or K, the spring constant K, is equal to 1,000 newtons per meter, and the mass is equal to 50 kilograms. And you can see that in the diagram shown here, we actually have two springs attaching this. So it's not just going to be a single K, we're going to have multiple K involved in our equation of motion. Okay, so the first thing that I think about is we don't know what the initial conditions were that started the motion of this oscillator. We only know what is happening when it passes through its equilibrium position, and that is that it has a speed of 2 meters per second. So in the equilibrium position, we can say here that the displacement is equal to 0. So that tells us that we have at 0 displacement, we have a downward speed of 2 meters per second. We can now shift time and call that time our new initial starting conditions. So although we don't know the original initial conditions that started this motion, we can use the information that we're given to form a new set of initial conditions. So let's just say we're going to form new initial conditions from information given. And with that being said, let's say that we'll say x0 is equal to 0, x of 0 is equal to 0. This is our x0 term, and then x dot of 0. And again, we've now shifted time backwards to start here. This is 2, and that's meters per second. And that should be 0 meters, 2 meters per second, and this 2 here, that's our u0. Okay, so I'm going to scroll back up here because we're now going to use equation 9 here. So we just said that our x0 is 0, x sub 0 is 0 meters. I'm just going to clean this up a little bit. So that tells us that the first term here, this cosine, that is not going to show up because the x0 term is 0. And so we are only left with the term with the sine in it. So from right here, we can say from equation 9, we can write that x double dot, in fact, we don't even need to write the equation of motion. We'll just say x of t is equal to 2 divided by omega 0 times the sine of omega 0 t. At this point, we now need to find the natural frequency of omega sub 0. And in order to do that, we need to write down the equation of motion. So let's just say to find, I'm going to rewrite that, to find omega 0, we need the equation of motion, or the EOM. Okay, so in this case, since we have two springs, well, first the mass times acceleration, that's going to be mx double dot. We have two springs here, so the restoring force acting on this mass for a positive displacement will be minus 2 times kx. That will be on the right side of the equation. We'll then bring that on over to the left-hand side. And so we'll get here plus 2kx, and that's equal to 0. So the standard form of the equation of motion is to bring all of the terms that depend on the x's or x dots or x double dots. We want to bring all of those to the left-hand side. And then everything on the right-hand side should not have an x in it. It should only depend on time, for example. Or it could be a constant, or 0. So from here, we can now write that omega 0 is equal to the square root of 2k divided by m, which is equal to the square root of 2,000 divided by 50. And that's going to be equal to 6.325, and the units on this are radians per second. It's very important that you pay attention to the units on this, because you will often find that people will report natural frequencies in terms of hertz. And so let's just do a brief aside here. So omega 0, this has units of radians per second. The natural frequency could also be expressed as f0, and this would have units of hertz, which is equivalent to cycles per second. And this f0 is equal to omega 0 divided by 2 pi, or omega 0 is equal to 2 pi times f0. So it's very important that you pay attention to the units here and that you use radians per second rather than hertz. Particularly when we come to computing inside of the sine function inside here. We're using omega 0, we're not using f0. Okay, so now that we know that, we can then compute what 2 over omega 0 is equal to. And this is equal to 0.316. And from there, we can get that x of t is equal to 0.316 times the sine of 6.325 t. From here, we now need to compute the acceleration. So we know the displacement. We're asked to find the maximum acceleration. And in order to find that, we're going to have to then compute the acceleration. And we're going to do that by taking derivatives. We'll start off by taking the first derivative of x with respect to time. That's our velocity, x dot of t. And that's going to be equal to, so when we take the derivative, we'll skip the constant, take a derivative of the sine. That gives us a cosine, then multiplied by the derivative of what's inside the sine, which is 6.325. Multiplied by 0.316 is equal to 2. So we end up with 2 times the cosine of 6.325t. And here we had to use our chain rule. Just as an aside, derivative rules that will pop up often in here in this class that you should review. First, the chain rule will pop up often. And second, product rule. Product rule will come up a lot as well. And there may be a few others that I'm forgetting, but these two are the ones that we will use the most often. So if you haven't dealt with derivatives in a long time, you should definitely brush up on those. All right, so from here we can then compute our acceleration, which is the second derivative. And in this case, we're going to have, well, we'll have 2 times minus sine of 6.325t. That's derivative of the cosine term. And then multiplied by the derivative of what's inside that cosine, which is 6.325. And of course, we're taking a derivative with respect to time. So our acceleration, x double dot of t, is then going to be equal to minus 12.649 times the sine of 6.325t. Great. So now that we have the acceleration, we're interested in finding the maximum acceleration. We have two approaches to doing that. So here we're going to say to find the maximum acceleration, we have two choices. So first, and probably the one that you might think to begin with, is that we can compute the derivative of the acceleration set it to 0, solve for the time, we'll call that t star, and then we can plug that into the acceleration. And sure, that certainly works, and there's nothing wrong with this approach. However, there's a second approach, which is that we could instead find the time when the velocity is 0. And then plug that into the acceleration. We're going to go through approach 2, and then we're going to use that to find our maximum acceleration. And then I'll show you that approach 1 ends up being the same as approach 2, except that we save some time by doing approach 2. All right, so approach 2. Okay, so we're going to start off with the velocity, which is equal to x dot is equal to x dot of t is equal to 2 times the cosine of 6.325 t, and then let's say that x dot of t star, that's equal to 0, which is then equal to 2 times the cosine of 6.325 t star. Since we have 0 in the middle here, we have 0 here, and a 2 here, we can just eliminate that 2. And then from here, we'll find that cosine of 6.325 t star, that's equal to 0, or 6.325 t star is equal to, in this case, now we're looking at, well, we'll start off with cosine inverse of 0, which is then going to be equal to 2n plus 1 over 2 times pi, where n here is equal to 0, 1, 2, and so on, repeating for infinity. These are the roots of the cosine function. And from here, we can then solve for that t star, which will end up being that t star is equal to, I'm just going to scroll on up because I had the number up here. It's going to be 2n plus 1, all of that multiplied by pi, divided by 12.649. All right, so that's our t star, and again, n is equal to 0, 1, 2, repeating on forever. So since we only care about one cycle, we're going to just choose a value of n and go with that. So since we only care about one cycle, we're going to choose, let's just choose n equals 0. Let n equals 0. And in which case, we're going to write that 6.325t is equal to pi over 2. The reason we're doing 6.325, and in fact this should be t star, 6.325 times t star, instead of solving for t star exactly, is because in the acceleration equation, which is up here, we have the sign evaluated at 6.325 times t. So if we can plug in just pi over 2 for that whole amount, we're going to end up saving ourselves some algebra and some calculations as well. So we'll substitute this into our acceleration, in which case we will say that, in fact, just to solve for t star, actually, let's just do that. This is equal to pi divided by 12.649. That's equal to 0.248, just in case you did want to do that. So x double dot, now evaluated at 0.248 seconds, is equal to minus 12.649 times the sine of 6.325 times 0.248, which is then equal to minus 12.649 times the sine of, well, in this case, it's going to be pi over 2. And the sine at pi over 2 is equal to 1. So in this case, we'll find that x double dot at 0.248, this is equal to minus 12.649, and this is meters per second squared for units. So because there's no damping in the system, the acceleration is going to alternate or oscillate from minus 12.649 to 12.649. So the maximum acceleration is going to be 12.649 meters per second squared. However, in this case, we have technically the minimum acceleration. So in that case, what we're going to do is instead try n equals 1. So let's say that this is the minimum acceleration. So let's try n equals 1. So in this case, we're going to have 6.325 T star is equal to 3 pi over 2, or that T star ends up being equal to, if we calculate this out, we'll get 0.7 for 5 seconds. From here, we'll plug that in, x double dot of 0.745 is equal to minus 12.649 times, the sine of, and in this case, we're just going to skip ahead and we'll have 3 pi over 2. In this case, this is equal to minus 1, which will cancel the minus out in front, so we'll get 12.649 meters per second squared. So thus, the maximum acceleration is 12.649 meters per second squared. Oh, oops. There we go. All right, so that was approach 2. Let's now apply approach 1, and you'll see how this ends up being the same. So just as a reminder, approach 1 is where we said we'll compute the derivative of the acceleration. We'll then set that equal to 0, solve for t star, and then we'll plug that into the acceleration. Okay, so first we're going to compute the derivative of the acceleration, which is known as the jerk. And compute the derivative of the acceleration. Again, with respect to time, this will be x triple dot of t. And like I said, this is called the jerk. However, we won't encounter it very often. And so if you go ahead and take the derivative, you'll find that this is equal to 80 times the cosine of 6.325t. We can then set that equal to 0. So we'll say x triple dot, let me rewrite that, of t star. We'll say that's equal to 0, which is equal to minus 80 times the cosine of 6.325t. Again, we can eliminate the 80, and therefore we end up finding that the cosine of 6.325t, that's equal to 0, and this is the same as approach 2. And so you can see if we go down this path, we'll end up finding the exact same result as in approach 2. Okay, that concludes this lecture. In the next lecture, we will start section 1.2, which focuses on damped oscillation.